Okay, we are going to try a virtual classroom today.
Can I take some homework?
So here we go. Just see how this works. All right. Okay, first thing I want to do is talk a little bit about the homework problem and kind of continue on where we were building last time with the heat transfer, which is partial differential equations. Okay, and then we're going to basically look at something even a little bit more specific. So I'll do an example problem, we'll do something a little bit more specific, and we'll take a little bit of time to talk about your guys' projects, okay? So let's start with an example. Okay. And here we have a PDE model, okay, and we have a heat transfer problem. Okay, and this will allow us to practice what we've been looking at before. Okay, so when we draw our diagram, what we have is we're going to choose a two-dimensional problem, okay, where we have a square plate, like a plate of metal, okay, for example. And we've got A here is that dimension, B here is that dimension, like we had in our homework problem, T equaling to 0, T equaling to 0, T equaling to a function of y, and T equaling to 0 on the top. Okay? And so for our rectangular region, we know that x is defined between 0 and a, and y is defined between 0 and b. Okay? That's a rectangular region that we have. Okay? So we're going to actually work through two cases. Case 1. So for case 1, what we're going to have is this t as a function of y. We're going to have a function that looks like this. Okay? So we have t of a and y is equaling to t0, and t0 is a constant. Okay? And over here you've got x equaling to a, okay, is where this boundary is. So this x equals to a right here matches up with this x equals to a up on our diagram there. Okay? So in this case we're saying here the temperature on the different sides, let's pick right here, this is our west side, east side, so this is 1, let's call this 2, north, 3 is our east side, and 4 is our south. Okay? So that's basically what we've got. Okay, case 2. Case 2, and it might be kind of hard for you guys to see that in the back. So I tell you what, I'll put case 2 up a little bit later when we get there, okay? So basically what we've got now, okay, we know that our equation, which we derived before, the Laplace's equation, is del squared, okay, or the Laplace of temperature equals to 0, okay? And in this case, we're going to say that this is a two-dimensional problem, so we're assuming there's no z component to this problem that we're working. Okay, so in this case we have partial derivative of t with respect to x plus t with respect to y equaling to 0. Okay, and this 0 over here, this means it's a steady state problem. Okay? So there's no instantaneous changes of temperature on the boundaries. Okay, so over here we've got a temperature that's a function of position along this y-axis, which is known. Okay, and then these are actually 0. Okay, so here we go. All right, so let's go ahead and start solving it. We know that, and what we should have written here on our cheat sheet, is we know that we have a product solution, Tx and y is equaling to a product solution, okay, phi of x, okay. So we've got a function of x and a function of y. So there's our product solution. So that's our solution to our problem. But what we're going to do is we're going to actually use our boundary conditions to make this solution fit this differential equation. Now, if we can't make the solution fit the differential equation, we know that we've done something and we really don't have a solution, right? Because we can't make it work out. Yes?
T's is equal to 0 on those on the west and north because
Yes.
there's no material.
Well, there's material here, right? But what we're saying on this plate is essentially, let's say that for lack of better expression, we've just put these particular sides in an ice bath to keep them at a constant temperature. That would be 32F, okay? That's the kind of thinking. We're holding these at a constant 0 temperature on the sides of the plate. Where we're actually affecting the temperature is along this side. And we can have all different kinds of distributions of temperature. We could have a constant temperature that's perfectly linear and constant all the way across this boundary up here. Okay, so we're talking about this boundary. So this matches up with this boundary. Okay? We could have a parabolic temperature profile. We could have different types of temperature profiles. What we're going to do is we're going to actually solve for what this temperature looks like. T is a function of x and y. We're going to find out what that is anywhere in this plate. Okay? So that's what we're trying to do. All right. So first steps. Okay? Number 1, we're going to separate variables. Okay? Actually, we're going to separate variables. Okay, so the first step we have here is we're going to actually go ahead and substitute this into our ODE. So we're going to end up with respect to x, we got phi double prime, okay, times, okay, no derivative here, plus, okay, we're going to take down the second derivative with respect to y. So we got, this remains constant. We don't take a derivative of that. We take the derivative of the second. Equals to 0. Okay? All right, so that's what we have there. Now we can go ahead and separate variables by dividing. Number 2, divide by our solution. To separate. Okay, so here what we do is if we divide by our solution here, t, let's do that. So we got now, we have, when we divide by our solution, we've got b double prime, okay, divided by plus okay, equals to 0. Okay, so at this point, now that we've divided by our product solution, we can go ahead and cancel out terms. Okay, those are the same, these are the same. Okay, and so what we're left with is our differential equation. So that's what we've got. Okay? So now we can see that this equation is separated. We have, I'm sorry, I did make a mistake here in nomenclature. I want to actually rewrite this. This should be dots, okay? Because this is a derivative with respect to time. So let me be consistent here. Dots are with respect to time, primes are with respect to x. Okay. Please correct that in your notes. Okay, so now what we have is we can go ahead and say that our phi double prime over phi, okay, equals to minus, okay, and we can set that equal to our constant, lambda squared, okay? Now, okay, so we talked about we have our solution, our product solution, and we're basically going to find the constants associated with that. Keep erasing this. Okay. So now this is our differential equation that we have. Now we can separate that into two separate equations because this one's a function of x only, this one's a function of time only. So let's go ahead and do that. Okay? So what we've got here is so there's our first equation. We'll call that 1. Okay? And here's our second equation. We'll call this 2, which is okay. Now, from our cheat sheet, we should know what the solutions to these are. Okay? We go look at our cheat sheet, and we know from the study of differential equations that for our first one we have a negative in there, okay? Cosine hyperbolic, lambda x plus b sine hyperbolic lambda x, okay? And over here, for equation number 2, let me actually separate these out a little bit. Okay, we have c sine lambda y plus d cosine lambda y. Okay? So there are two equations. Okay? So now at this point, we want to check, so we know that this is the case for lambda not equaling to 0. Okay, this is our general solution. But we also need to check the null space. Okay? Because let's check and see what is our solution if lambda equals to 0. So phi for lambda equals to 0, we get, okay, if we integrate twice, the first integral, you're just going to get c1, we'll call it. Let me make sure I'm being consistent with the nomenclature I have. Okay, I call it H. H1, okay? H1 x plus H2, okay? And over here, if we let lambda equals to 0, okay, we get basically the same thing I used C. So C1y plus C2, okay? So, now then, our total solution, remember, our product solution is T of x and y equals to phi of x. Y. Okay, there we go. So we're going to go ahead, use our general solution. We're going to plug these terms in to get our total and complete solution. Okay? So let's do that. Because of linear dependence, we got our constant terms and we have our sine and cosine terms. So T of x and y now then is going to equal h1x plus h2 times c1y plus c2. Okay? Plus a cosine hyperbolic lambda x plus b sine hyperbolic lambda x. Okay? And then we've got c sine lambda y plus d cosine lambda y. Okay, so there's our total solution now. Okay, now we're going to use our boundary conditions to eliminate constants and balance the equation so this is in fact a true solution to our heat transfer problem. Okay, so we're going to make sure that this general solution now works by forcing it to work by applying our boundary conditions. Okay, so first let's try the, let's see which one I did first here. Let's go ahead and do the west face. So the west face, okay, we're going to do that first. So our boundary here is on this west face, okay, we know that the west face is defined by x equaling to 0, right here, okay? And y is, it's always y, okay? So we have, for our west face, we have t as a function of x equaling to 0. Let's see here. Which one did I do first? Did I do west? Wait a minute, I don't think I did west in the notes. So let me be consistent with my notes here.
I think you did east first.
Yeah, because I have
X is equal to A,
0 for y is what I did in here. Okay, so I guess I did this one first. So I did the south face. Let's do the south face first. And the order of these isn't so critical. Let me just be consistent with my notes. Okay, so the south face, we're going to do that first. So for the south face, you got t of, make sure I did this right, x. Okay, so x is always there, and y is equaling to 0. Okay, so that equals to 0. So x is always there, okay, and y is equaling to 0. So that defines our south face. Do you understand what I just did there? Okay? And I took some time to think through it because I want to make sure, yes, this makes sense. Okay, so the south face. So we set that equal to 0. Now we actually plug in here. Okay, so we know that y is the one that's being zeroed. So I've got now h1x plus h2. Okay, that's our first term. This term, y goes to 0, so I just have c2 now. Okay, and so now we're going to add all this in, and we know that x is, y is 0, so the first term remains a cosine hyperbolic lambda x plus b sine hyperbolic lambda x. Okay, so there's your first term. The second term, we know that we have 0 for y, so sine of 0 is 0 plus d. Okay? So now we have to choose. We have to make some choices. We know that this equation has to be 0, term by term. Because of linear independence, we've got two separate terms. We've got to make sure this is 0. So, here we go. So we're going to basically, our idea is we want to retain the most information in our solution. Okay, that's the criteria when we're looking at these two terms. So let's look at these two terms. Let's look at the constant term first. Okay, constant and x. So we have a choice. Either h1x plus h2 equals 0, or c2 equals to 0. Okay, keep in mind that's for all time. So we're looking at this term. Okay, so the one that's going to actually retain the most information is c2 is equaling to 0. So that's what we're going to select. Okay, because if we make this term equal to 0, okay, we get rid of we get rid of some more, we get rid of more information, we get rid of x information, we throw it away, okay? So we're going to keep that. How about this term over here, okay? We have a choice. We can either let a cosine hyperbolic lambda x plus b sine hyperbolic lambda x equal 0, or d equals 0, okay, for all time. So if I make this 0 for all time, that really gets rid of quite a bit of information, okay? All right? So we're going to allow d to be 0. Okay, so we got c equals to 0 and d equals to 0. So we can rewrite our equation now. So now what we have is t of x and y, after applying this boundary condition, these boundary conditions is, we have c2 is 0, so we got h1x plus h2 times c1y, we got rid of c2, plus, okay, we let d go to 0, so now we got a cosine hyperbolic lambda x plus b sine hyperbolic lambda x, okay? We know d is 0, so we just have c sine lambda y, okay? Because d is 0, that term goes away. So now there's our general solution after we've applied the south boundary condition, okay? Now then, as we take a look at this,
Question.
yes?
Is it 0 plus d? On the-
0 plus d, yes, 0 plus d, because sine of, so if I look up here, when I put in my boundary condition, y is 0, sine of 0 is 0, so 0. Cosine of 0 is 1, so that's where I got my d in there, okay? All right, so this is where I'm at right now. Let's keep going. Oop, did somebody need that? Okay. All right. Go ahead and keep that one and erase all this. All right, so that was the south. So let's see, which one did I do next? Okay, it looks like in my notes, to be consistent with that, d 0, y equals to 0. Okay, that's the next one, which is, so x is 0, and all y, that's this boundary condition, so this is the west. That's the west boundary condition. We were calling that 1. Okay? So now we're going to actually go ahead and look at that. So if we apply x being 0, then we just get h2 c1y, okay, plus okay, so we got x is equaling to 0. So we just have cosine hyperbolic of 0. So you just have a, okay, and b sine hyperbolic of 0 is 0. So I just have this a here times c sine lambda y. Okay, so that's what I've got there.
How about a question?
Yes.
Now we're basing it off on this equation that we...
Correct. Yep.
And then when we finish this one, the equation we get, we will use it for the north side?
Exactly. Yep. So we're just basically step by step solving for our constants as we go through this process. Okay. So now in this case, all right, I have a choice here. I can have, so I said x was equal to 0, right? So I have h2 equals to 0, or I've got c1y equals to 0. Well, okay, so the best thing I can do is let h2 equal to 0, right? That retains the most information there. And over here I've got a constant sine lambda y equals 0. Okay, we're operating on x. So all I can do here is allow a to equal to 0. Because I don't want to delete, I don't want to get rid of this term. So allow a to be 0. So now my solution is going to be, let's write this, tx and y is going to equal to, so now my h2 is 0. So now I got h1x, okay, c1y, okay, plus my a is 0, so this term goes to 0. So now I've got b times the sine hyperbolic of lambda x times c sine lambda y. Okay? So that's where I'm at now. So now, if I take a look at this here, okay, I've got two constants that I can combine here in a little bit. Okay, so we've written up our next step. Let me erase that one. So now, let's see, so now we're going to do the north next. Okay, and so for the north, okay, so x is always continuous on the north, and y is always b. So y is set at b, and x is always there. So we're going to have t of y equaling to b, so x and b equals to 0. All right, so now we've got, here we got h1x, okay? And I got c1 times b, okay? And then I got over here plus, so I'm going to put in for b. So I got b. I can combine these. Let's actually combine these two. Let's call this now, let's see what I call over here to be consistent. We're going to call it C star, okay? So we'll call it C star. So we're going to call this C star times, combining those two constants, times sine hyperbolic lambda x, okay, times this term, which is sine lambda times b. Okay, so now I got to choose. All right, so I've either got h1x equals 0, but I'm actually operating on this term. So this says that c1b equals to 0. So now I got c1 equals to 0 for that term, okay, to retain the most information. But guess what? I don't have any more information, right? Because when I put c1 equals 0, it's 0 for all time. So there is nothing in the null space. So lambda, we don't have to worry about lambda being 0 being part of our solution here in this case, for this problem. So this term goes away. In this case, right, we've got either c star equals 0, or we have sine hyperbolic lambda x equals to 0 for all time, which sine hyperbolic lambda x, it's not always 0, right? Think about how sine hyperbolic looks, okay? So it's not always 0 in general, so we know that's probably not a good option. Okay, and then the other one is, or we have sine lambda b equals to 0. Okay, well, that seems like that one we could So this zeroes out the whole thing for all time. This one zeroes out the whole thing for all time. This one doesn't. So that retains the most information. So we want to go with that one. Okay? So this, when is sine lambda b equal to 0? Sine is equal to 0 at when lambda b equals to n pi. Okay? So from this we have lambda n equals to n pi over b. Okay? So if we put that in, it's satisfied, and this term now is satisfied. This term went away, so now we just got t of x and y is equaling to, okay, so we have c star, and now our c star, right? Okay, so we actually chose this one to be 0, so I'm going to box that, okay? So we chose that one to be 0, okay? So now our c star, since we have a lambda n here, we're going to change that to c sub n, okay? In fact, let me change it to a different term, just so you guys are familiar with it. Instead of calling it c sub n, how about we call it b sub n? B sub n, okay? Like in Fourier. So we can call it any constant we want, but so we got b sub n times sine lambda n, okay, x, okay, times sine hyperbolic lambda x. Oh, this should be y. I'm sorry. Yep, sine lambda y. Okay, so I've done the substitution there. Okay, in this case, I need to put a comma and say for n equals to 1, 2, 3, and so on. Okay? So there's what I've got from here. Okay? So I can actually put this in sine lambda b. Okay, so now we're going to finally let's go ahead and put in what our lambda is. So erase some of this. So what we've got now, t of x and y is going to equal to summation n equals 1 to infinity. Okay? I want to write it exactly like I have it here. So I've got b sub n, okay, sine n pi, so I'm going to substitute in now for lambda, over b, okay, so I've substituted in for lambda, times x, or wait, times y, sorry. Okay, there's my first term. My second term is sine hyperbolic n pi pi x over b. n pi x over b. Okay? So there is my solution. Let's go ahead and erase. All right. So now, what we have here, okay? So as we're looking at this, this looks kind of like, if you take a look at this term, okay, I've got a sine term here, I've got this term, and I've got a hyperbolic term there, okay? So that kind of, ooh, I have, okay, this kind of is starting to look like a Fourier. So let's let we're going to apply our next boundary condition. But let's like b sub n sine hyperbolic n pi. Let me do one more step first. Hold on, let me do one more step before I write this down. Okay, so our final boundary condition, okay, we're going to look at is t equals to f of y, and we said t, so here's our final boundary condition, t, which is f of y, is a, so let's see, here's a, and all y, okay, on that surface, y on that surface, so if t, a, and y equals to t0, okay, which equals to function of y. So this is a function of y only. So what this is saying is, over here, it's not a function of x because it's on a, x equals to a. So I have this temperature that's a function of y over there. So we're going to see what this temperature as a function of y does to our plate in terms of heating everywhere in the plate. Okay, so here we go. So we got this equals to summation n equals 1 to infinity b sub n sine n pi y over b times sine hyperbolic n pi a over b. Okay, do you see what I just did there? I substituted because I got a here. Okay, I substituted in for my x. Okay, so that's what I've got now. Okay, so now, if we take a look at this, this looks an awful lot like a Fourier. So we can rewrite this. Function of y is equaling to summation n equals 1 to infinity, okay? And we've got b sub n, which is a constant, times sine hyperbolic n pi a over b, which is really a constant as well, times sine n pi y over b. Okay, so the y, so this term right here, making typo mistakes here, let me fix that. Okay, rewrite that again. Sine hyperbolic n pi a. Okay, I need to stop for a second. Okay, stop, take a breath. All right, let's try it again. Okay, here we go. All right, so sine n pi y over b. There we go. This one's a function of y, okay? This is just a constant term. Okay, now remember, I'm going to erase this in a second. Remember, from Fourier series, f of y just equaled, now this should be from your cheat sheet, okay? It was a sub 0 plus summation n equals 1 to infinity. Okay, why don't you guys look that up? What's the rest of this? What's the Fourier expansion look like?
an sine.
Okay, a sub n times sine, actually it's a sub n times cosine
N pi over
pi
L.
x.
X over L.
We actually have y here, so we'll put y over L plus, what's the next term?
AB or BN
B sub n sine
N pi Y over
n pi y over L. Okay, that was our Fourier expansion that we had before, right? So what does this kind of look like right here? Just this term right here.
the sine term.
You got a constant and a sine. Okay, so here's your L. You got L as B. Okay, so you go from 0 to B, right? So that's your 0 to L. All right, and these terms don't exist. So what we call this is we say this right here is a Fourier sine series. Okay? That's what you've got right here. So I'm connecting that to what we know from before. Okay, so we're going to use what we know about that. I'm going to go ahead and erase what we had on our cheat sheet. And we're going to use what we know about that to solve for our particular case. So let's just call this right here E sub n, just for lack of a better term. So then we're going to have f of y equals to summation n equals 1 to infinity E sub n times sine n pi y over b. Okay? So there's what I've got so far, all right? Okay. So now then, I'm going to do some erasing. Wonder if I need to save any of this for you guys. I think not. So this is our last boundary condition we're working with here. Okay, so now what we're going to do, we're going to solve for E. So we're going to solve for E sub n. Okay, what this is like, okay, is this is like solving for B sub n in a Fourier expansion. Okay, so we can use our formulas. So in this case, we have E sub n is equaling to, just using our constant term to solve for the constant, 2 over L, 0 to L, f of y, sine n pi y over L dy. Okay, so we substitute in, we've got 2 over L, integral from 0 to b, function of y, sine n pi y over L dy. Okay, well, we know in this case that L is just b. Okay, let's take our next step here.
Did you mean to have integral from 0 to L and integral from 0 to B?
You can do it that way, or you can do it with, you can also do the limits from d plus 2L, and then change that. So you can do it either way, I write it this way because you might see it this way in some texts, you might see it the other way in other texts. Okay, so do I want to erase that yet? Okay. So before we take the next step, remember what we had before? We said that, let me just write up again, we had t of a and y, this is how we got this, equaled to f of y. And we said that f of y was equaling to some constant t0, right? t0, right here. Okay, so here's our t0. It's just a constant. Okay, so in this case we can actually substitute in and solve. Let's go ahead and do that. So when we do this, we get equals to summation E sub n sine n pi y over b n equals 1 to infinity. Okay. Erase this one. Okay, so back to our integral equation, e sub n equals to 2 over b, 0 to b, t0, so I'm just substituting it in now, t0, sine, so I put the function of y, here's the function of y. Okay, so here's my, back to my Fourier integration here. So I got sine n pi y over b dy. So when we solve for our constant here, we're going to get minus 2 t0, okay, over b cosine n pi y over b, okay, this whole thing is over n pi over b, evaluated from 0 to b. Okay, so I took the integral there. So what do we got here? We got e sub n equals to minus 2 t naught over n pi times minus 1 to the nth, like we looked at before. Okay, we just looked at our cosine term. We can represent that because it varies. N equals 1, n equals 2, n equals 3, minus 1. Okay, which this equals to 4 t0 over n pi 4 n equals, or n odd, and 0 for n even. Okay, I'm going to stop here for a second. Okay. So, yes, let's stop here. Let's talk about this. Yes?
How come it goes from -1 to the n?
Here?
Yeah, how do you do that?
Okay, so I was just looking at this. Okay, I was just looking at this. So when I substitute in for a cosine, I have a 0. Cosine of 0 is 1. I got a negative over here. Okay, so I got, or cosine of 0 is -1. So I got this one. And then cosine b over b. So this is just going to be, this is just going to turn into, for the b limit, cosine n pi. Okay, so if it's cosine n pi, your first one is cosine pi, cosine 2 pi, cosine 3 pi. And so if you look at it, it alternates between -1 and +1, -1 and +1. So if you just put it to the n to the exponent, put -1 to the exponent, it's equivalent to having cosine n pi. Okay? And so it's just the standard convention that you're going to see, generally introduced for computers. Okay? Because it was easier to put in a -1 with a little exponent than represent it by a cosine. Okay? So here, what we have done is we have taken what we had on our cheat sheet, basically, okay, right here, looked at our period, our 0 to L is 0 to B, okay, and we integrated over our period where it's valid from 0 to B, okay, and our equation said we just put our function in here. So our function is right here, t0. It's the value of our forcing function. Just a simple square function. Multiply times sine, and we integrate, and out comes our value, just like we did before. Is everyone okay with that step? I can rewrite it another way. Do you feel a little uncomfortable with that? This is Fourier, okay? We're using Fourier. So before, let me actually erase this. I'm on purpose taking a moment here to pause. go ahead and write out our general solution for this case. So now we've got remember before we had t of a and y equal to, I'm putting this back up, n equals 1 to infinity of this e sub n, okay, that we were trying to solve for, sine n pi y over b. Okay, so that's what we were doing by applying Fourier, okay? So now, we know that. There's another, I wish I had more room to write all this out. Okay, we know that E sub n is equaling to 4 t0 over n pi, which equals to, remember before what we took, we had b sub n sine hyperbolic n pi a over b. I know this is a little bit hard to follow because there's a lot of steps in here. Okay, because we said this term right here, remember, we said from this equation, before we said let E sub n equal to b sub n sine hyperbolic n pi a over b. Okay, so I just set that equal. Okay, so this is E sub n. Now I'm going to go ahead and go the next step. So now I got b sub n equals to 4 t0 over n pi times 1 over sine hyperbolic n pi a over b. Okay, there we go. I got b sub n now. All right. Finally, last step, let's substitute this whole thing back into our general equation. So now, our general equation is going to be t of x and y equals to summation n equals 1 to infinity 4 t0 over n pi sine hyperbolic n pi x over sine hyperbolic n pi a over b times sine n pi y over b. That is our solution. Doesn't that look nasty?
Should we have n pi x over b for the top part?
N pi x over b. Yes, thank you very much. N pi x over b. N pi. There we go. So we can see here that we got a constant and we got a hyperbolic x function. So along the x, we got a temperature profile that's going to behave like a hyperbolic. And then we've got also, in terms of y, when we're moving in the y, we've got something that's going to be like a sine. That's what the temperature is going to look like. I can put in any coordinate now, and I can get the temperature in that plate. Okay. You guys have any questions about this? This is kind of about as bad as it's going to get in 2 dimensions. Okay? We're not going to do 3 dimensions in here. We could, but 2 dimensions is bad enough. Okay? And really, it's a matter of keeping track of everything that you're doing, and we're really using everything we've learned so far. We're using Fourier, we're using our differential equations, we're using a little bit of everything, okay? So we did case 1. Where are we at now? So, case 2. So now what happens, let me just ask you one question here. What happens if you're going through this process and you're trying to get your solution and you find out that you put your boundary conditions in and you don't get a solution? Your only solution, you get a 0. What do you think that means? Maybe you don't have a good solution, huh? So here's my recommendation. So if you did it with lambda squared, okay, then do it negative lambda squared, okay? Which should switch your sign. So instead of having, so let me explain what this means, okay? Let me erase this one. Because remember, okay, let's go back a couple of steps here to our general equation. And this is how it's done, guys. It's kind of a trial by error. Remember we said this? Phi double primed over phi equals to minus over equals to lambda squared. Okay? That's for positive lambda. Okay? We didn't check negative lambda. If we get a solution, we're good. We checked 0, lambda equals 0. We checked positive. We didn't check negative. Now, if you go down that pathway and it's not working, then you know that's not the solution and there's nothing there, so you have to switch the signs. Well, what does that do to me? Okay? What that does is, if I switch the signs that I do for lambda negative, so first I had phi double primed minus lambda squared equals to 0, right? What it's going to do is it's going to flip the sign. This is case 1, that's from here, okay? And you're going to get this, right? This one, double prime, plus all right? But for, okay, so this is for positive, so this is for lambda squared, okay? But for negative lambda squared, what you're going to get is, you're going to get plus lambda squared. And this one is going to be and it's going to switch your solutions. So now you're going to get lambda x. Should be using dots here. Sorry about that, guys. It's time. Okay. So you should be getting b cosine lambda x, and your other one here now becomes c sine hyperbolic lambda y plus d cosine hyperbolic lambda y. Okay? So when you actually apply your boundary conditions, guess what's going to happen? You're going to get a different, when you're going through the process, the boundary conditions are going to affect your general solution differently. Okay? So that is the standard procedure. Is if you get stuck on one, you pick one and you go with it. If you get stuck, you find out that is not a solution that works. And so then you go with the other one. This is standard procedure, guys. Okay. Some people will teach to do them all at once. So I did the constant terms, the null space, which is land equals 0, and then I did one of them together. And generally, I mean, you got a pretty good chance of catching them. The other thing you can do is do this one, and do this one, all three, and you do them all three and check them all at the same time, which just takes a little bit longer to do it all. And if you don't need to do it all, why do it all, right? And there was a question you guys had in the back? No questions? Okay? All right. So this is what we have, guys. Now then, what if and this you guys will have something very similar to this problem in your homework, okay, that we just did. But what if we have, for our final, we have t of a and y is equaling to sine pi y over b, which looks like, on the end over there, so here's our temperature profile as a function of y. Here's x, this is x equaling a. So this basically, right here, this boundary is this boundary. Okay? What if we have that? Okay. Well, what does that look like to you guys? It's just a sine, right? So if we're going to approximate this with the Fourier, okay, that looks like a square. Remember Fourier, I'm going to turn it on the other side. Remember we did Fouriers like this? Okay, so in this case, if I'm trying to approximate, okay, with a sine, my first term, okay, might be something like that. That's my first order approximation to use a sine to model this square wave. Okay? If I take another term, okay, I'm going to have something like that. That's two terms in my Fourier series for sine. And I'm going to keep doing that until I match the square wave. But in this case, look, just one term matches that pretty well, huh? So that should give us a clue as to what we're going to have. Let's actually look at this, okay? So if we look at this Fourier series, 4t0 over pi times sine pi x over L plus, we get plus 1/3, and we expand it out, sine 3 pi x over L. So now I'm putting in these terms, okay? Then you get plus 1/5 sine 5 pi x over L plus on into infinity. So there's your terms that I'm talking about here that I just drew, okay? Here's your n equals 1 term, n equals 2. Wait a minute, what did I do here? N equals 1, n equals 3. I think that's what I put here. And n equals 5. Okay? All right, so for our problem, we actually have f of x equals to 4t0 over pi times sine pi y over b plus 1/3 sine 3 pi y over b plus 1/5 sine 5 pi y over b plus, okay? And why do we have just the odd terms? Remember what we said is for only for the odd terms did our solution exist. For the even terms, it was 0, correct? That's why they're missing. So if you remember what we wrote out before, we said E sub n was 4t0, what was it?
Negative 2t0.
Was it negative 2? Whatever, okay, negative 2, was it 2? And I forget. 2, so I had negative 2t0
Over n pi
n pi.
times the quantity.
Okay, and there was a quantity with signs and stuff in here, right?
Is
Which I
that-
won't go into all that. There's something in here. Something like 1 squared, or n minus 1, or something like that, okay?
Yeah.
All right, so what we're saying here is we've got our first term, and we said that when we looked at this, we said we had, and we'll end with this, because I know we're, yeah, almost there. Okay, we said we had, where were my notes on that? Okay, so I had 4, so this turns out to be 4t0 over n pi, or 0. Okay, this is for odd, and this is for even n. Okay, so that's what I did here. I just want to show you all the details. I just expanded this out. Okay, so in this case, we can pretty much generally write out what our solution is going to be. Our solution is going to be we don't have to apply Fourier because we know what our solution is. Okay? So before we had, take our old solution here. Let's see if I can do this like this at the same time here. Our previous solution was Tx and y equal to summation n equals 1 to infinity 4t0 over n pi times, and actually I'm going to write it this way, okay, so then we got, I'm going to write it this way, 1 over sine, this is the constant term again, hyperbolic, n pi a over b times sine hyperbolic n pi x over b times sine n pi y over b. Okay, so that was our previous solution. Okay, now for our case, take a look at this. Okay. Okay, so all we do is we just take this first term in our Fourier series expansion. So our actual solution is going to be t, I'll finish this next time, x comma y equals to t0 sine pi y over b, which is the first term to our Fourier expansion, because this term right here very well matches our parabolic distribution for temperature. Okay? times sine hyperbolic n pi x over b over sine hyperbolic n pi a over b. Okay? So I'll work on this a little bit more next time. But you can kind of see that just by looking at this first term, that you can represent it by this sine function. Let's look at this a little bit more. I want to explain and take a little more time with that next class. All right.